So we're continuing at the examples you were trying after the last video, and here are the answers. So the first one, we've rearranged PV equals nRT to give us V equals nRT on P, subbed in the numbers, remembered to show that we have converted degrees Celsius to Kelvin. And you can show that in the equation if you wish, or do it off to the side. Please do show this step with your substituted numbers. Please don't just jump to the answer. You need to show your working, and this is the line that examiners would be looking for. And then it simplifies to 59.95 litres, but we are working with 3 significant figures, and so it is 60 litres. As 60.0 litres. The next example, we wanted to calculate a pressure. So we now have P equals nRT on V. Substitute in the numbers again, change the temperature to Kelvin, and that comes out to 3 significant figures as 208 kilopascals. Number 3. The temperature. Now remember that your temperature, when you've rearranged the equation and it becomes PV on NR or RN, whichever you prefer, sub in the numbers, that temperature is coming out as Kelvin. And a lot of the time they want you to give the answer in degrees Celsius. So there's no harm at all in giving your answer first in Kelvin and then converting it to degrees Celsius. As long as you do that correctly by subtracting 273, you won't lose marks if they didn't want it in degrees Celsius. But if they did want it, well, you know, you've got to make sure you've given the answer that's required. Finally, and minus 13 degrees on top of Mount Everest, perfectly reasonable temperature. Matter of fact, it's a balmy day. Right, finally, in question 4, it was a simple one because it was at SLC. So when you see that, you know to use N equals V over Vm, rearrange to get volume equals number of mole times molar volume, sub in the numbers, and you initially come out with 0.632 litres. I'd recommend anything less than 1 litre, change it to millilitres. Just as a rule of thumb, once again, you might not lose marks, but there I would expect with a question like this, probably said in the question to give the answer in millilitres. So there's those 4 examples. I hope you did well on them. That's the end of section 3.2. Now, a reminder that you should be writing down the main points that you're learning in each section to give yourself a chance, number 1, to check that you were actually paying attention, and number 2, as the beginnings of a summary. It could even be your whole summary, but I really want you to do this all the way through this year. Many of you started it with me last year, and I think you agree that it's a good thing. Now, there's an Ed Rollo video that covers this work, and I do want you to be watching that in addition to my videos, please. Right, on to section 3.3 and 3.4. Now, these are the calculations in which you'll be working out moles of gases. So you now have 2 equations to calculate moles of gases, depending on whether it's any old temperature or whether it's standard conditions, SLC. So we're using the same rules for stoichiometry as we did last year. And so I'll be going through those same steps. Now, we don't have aqueous solutions at this stage of our course. But by the time you get to the end of the year, you will have done aqueous solutions as well. So this point remains valid. Always note to yourself whether the volumes in the question are solutions or whether they're gas volumes. So here's our 6 steps to stoic success. You'll remember that rather annoying catchphrase. We start out with a balanced equation, and more often than not in year 12, you'll be expected to write the balanced equation yourself. In the question, identify the known quantity. So this is the quantity that you have all the information available to be able to calculate mole. And identify the unknown one, the one that you need to find the volume for, or the moles, or whatever it is. Then at step 3, we're going to start with the known and we're going to calculate mole. So if it's a gas, we now know the gas formulas. If there's a mass, then it's N equals little m times big M. And that formula is in your data book. So from the equation then, at step 4, we write out the molar ratio using the coefficients in the equation. Then use that molar ratio to work out the amount in mole of the unknown. And then finally, convert it to mass if you need it, or to volume of solution later in the year, or volume of gas, which is quite often the case now. All right, so this is putting it all together. So there's the formulas that you're going to want to be using. Now, these formulas are all in your data book, but the information you don't have is this one, that if it's a solid, you're going to use that equation. If it's a solution, you're going to use that one. And if it's a gas, you're going to use one of those two. In your textbook on page 83, you have another graphic which shows you the relationships to use. So you may prefer that. And let's start an example. Right, I've tried to keep my color coding the same as on the earlier slide. So in this example, we want to find the mass of carbon dioxide that's produced when 500 grams of octane, remember octane is C8H18, undergoes complete combustion. So we start off with the balanced equation. Notice I've done 1 mole of octane here, and so we've got 25 on 2 mole of oxygen. And it's making 8 mole of CO2 and 9 mole of H2O. Now, this one is the best one for the job because all the question asked for was the mass of carbon dioxide produced. So we only need the octane and the carbon dioxide. So our known is our 500 grams of octane. You might highlight that in your question, or you might write it out separately, whichever you prefer. The unknown is the mass of carbon dioxide, and so you'd highlight that in a different color. And then we calculate the moles of octane, 500 divided by the molar mass of octane, which you would be expected to work out, and you may not even be given a separate mark for that because we're in year 12 now. And so you've got 4.39 mole. The molar ratio, now it's really funny that I kept that in because this is the molar ratio in our equation. Obviously, I must have formerly had this with the 2 to 25 ratio. So it's 1 to 8. We don't have 1 mole of octane. We've got 4.386 mole. So we are going to multiply that number, the 4.386, by 8. So we divide by the 1 and we're multiplying by the 8 and we get 35.09. Keep those numbers in your calculator, and so you won't round off the 35.09 for the next step. You'll use what's in your calculator. I've just written it down there for convenience, and you multiply by the molar mass of carbon dioxide and we get 1,544 grams, but the significant figures are only 3, so it's 1.54 kilograms. Or you could, I don't know why you would, but it would be maybe okay to write it as 1.54 by 10 to the 3 grams. But honestly, 10 to the 3 grams is a kilogram. Better to use the correct units. Here's a second example. Find the volume of octane at SLC that will enable complete combustion of the 500 grams of octane. So this time we want the volume of oxygen. So our known is the octane still, our unknown's the volume of oxygen. We've still got the same number of mole of octane, the 4.39 mole, and our molar ratio this time is 1 to 25 on 2. So we take our 4.3, now you see I've used the correct number from my calculator, right? 4.386, and we multiply it by 25 on 2 because that is the coefficient for oxygen, and we get 54.8, or the appropriate number in your calculator, multiply it by 24.8. Now you'll see that I've got a more accurate figure here, 1,359.6 litres, but you need 3 significant figures because of the 500 for the octane, so this becomes 1.36 by 10 to the 3 litres. So that's that example. Now, there's a special case in reactions with gases. It's a very easy special case and is worth looking out for. If all of your reactants and products are gases, and they're all at the same temperature and pressure. Now, this will be stated in the question that the temperature and pressure has remained constant. Then we invoke Avogadro's law, which says that volume is proportional to number of mole. So this gives us permission to treat volumes as amounts. So we can plug in the volumes as though they were moles. So let's look at an example here. So we've got some methane being burnt in a gas stove. We've got 50 ml of methane. Where's the pressure? There's the temperature. We are being asked for the volume of O2. Notice it's the same temperature and pressure. So they haven't explicitly said constant temperature and pressure. They've given it to you with the numbers. And then the second one is asking for the volumes of carbon dioxide and water. So we start with our balanced equation here. And our molar ratio of methane to oxygen is 1 to 2. So we just plug in the volume as though it was a mole and do the 1 to 2 ratio, and you've got 100 millilitres of oxygen. And that's your answer to A. Job done. In the second example, they're interested in carbon dioxide and water. So once again, using the molar ratios, which is 1 to 2, you've got 50 ml of carbon dioxide and 100 ml of water. Once again, just using the volumes as moles. So these are very quick questions. They could be multiple choice, or they could maybe be just assigned 1 mark. So keep an eye out for those. They're very important. Right. As at the end of the previous video, here's some examples for you to try. Have a go at those 3, and then at the start of our next video, I will go over the answers.